Welcome to the Professional Engineer Podcast. This is going to be a bit of a shorter podcast as I experiment with the best format for these solo podcasts and as I continue to build up my confidence to bring on guests. My goal is with episode number 12 for that to be my first episode with a guest on it, and then for the majority, if not all of the podcasts beyond that point, to continue that. In this first introduction to one of the 14 grand challenges for engineering in the 21st century, I chose nuclear fusion. I did this because it seems like almost every day we read about some new breakthrough in science. And over the last 2 months, nuclear fusion has made waves with headline articles. It saw a Chinese-based reactor sustain a 17-minute reaction at 126 million degrees Fahrenheit, and a European-based reactor generate 59 megajoules of energy in a period of 5 seconds. And both of these reactors are in support of a larger nuclear fusion reactor that is currently under construction in France through an international collaboration of 35 countries, including the United States, the European Union, Russia, China, India, Japan, and Korea. So let's talk a little bit about these breakthroughs. First, I just have to say, what the heck is nuclear fission? And to put it frankly, it is the condition inside the sun. And mankind is trying to recreate this reaction to generate energy from it. So now more specifically on nuclear fusion, let's draw two parallels. One is nuclear fission with an I, and then we have nuclear fusion with a U. So nuclear fission is what nuclear power plants today use. Essentially, they take unstable isotopes, so this is like the uranium, and they have high atomic numbers, and these are dense, and they split that nuclei by like shoving neutrons at it at very high speeds. And to separate that nuclei into two lighter nuclei, generating heat or energy in the process. And then they use that energy to heat up water to power turbines and ultimately generate electricity. Now, nuclear fusion is the opposite. Instead of splitting the atom, this involves fusing the atom, fusing these two nuclei together, which in turn releases a significant amount of energy, which then can be used to heat water and generate electricity by spinning the turbines. So we already have fission technology, but this generates nuclear waste and a significant amount of nuclear waste. But the idea is with nuclear fusion, it will generate much less nuclear waste and is considered a renewable energy source due to the abundance of the fuel used in fusion. And I think rather than me trying to do best explaining, I'm going to take a quote right from the ITER, which we'll talk about later, but that's the coalition of those 35 countries. Nuclear fusion is the energy source of the sun and stars. In the tremendous heat and gravity at the core of those stellar bodies, hydrogen nuclei collide, fuse into heavier helium atoms, and release tremendous amounts of energy in the process. 20th century fusion science identified the most efficient fusion reaction in the laboratory setting to be the reaction between two hydrogen isotopes, deuterium and tritium. This DT reaction, deuterium-tritium fusion reaction, produces the highest energy gain at the, quote, lowest temperatures. And by lowest, it's not cold temperatures. It's still extremely hot temperatures. But hot's an understatement. Anyway, 3 conditions must be fulfilled to achieve fusion in a laboratory. 1, very high temperature on the order of 150 million degrees Celsius. 2, sufficient plasma particle density to increase the likelihood that collisions would occur. And 3, sufficient confinement time to hold the plasma, which has a propensity to expand within a defined volume. At extreme temperatures, electrons are separated from nuclei and gas to become a plasma, often referred to as the 4th state of matter. Fusion plasmas provide the environment in which light elements can fuse and yield energy. All right, so that was a lot of kind of technical jargon, but I think That is enough for an introduction from a guy who is not a nuclear physicist. So let's talk about those advancements in the news. We are going to start with China's East Reactor, which stands for Experimental Advanced Superconducting Tokamak. East. EAST. And keep in mind that word tokamak, we're going to talk about that at the end here. And that's the type of reactor, the type of nuclear fusion reactor they are using. So what they did is they superheated plasma to 126 million degrees Fahrenheit for 17 minutes, which is a little under 5 times the heat of the sun's core, which the sun's core runs about 27 million degrees Fahrenheit. And they broke a previous record back from 2003, where France held similar temperatures for about 6 minutes. And by the way, 2003, so almost 20 years ago, it took them to break this record. Keep that in mind, because what is currently being built is being built with modern technology. So this breakthrough focused around the duration at which they were able to sustain these temperatures. It wasn't so much that they sustained this temperature for just a few seconds. This happened for 17 minutes. And that is what makes this significant. And this same reactor in China, by the way, broke a similar record where they achieved the hottest ever fusion temperature at 201 million degrees Fahrenheit for only 101 seconds. So this makes me ask a lot of questions. And at top is, how is it possible to have such a high temperature and not just melt everything? And the answer to that is a magnetic field, which we'll talk about more at the end of the podcast when we talk about what a tokamak is. And then the second question is, why is this significant in the nuclear fusion realm? And so the leader of the experiment, Gong Jianzhu, says the recent operations lays a solid scientific and experimental foundation towards the running of a fusion reactor. So as mentioned before, one of the more important challenges for nuclear fusion is maintaining that superheated plasma for a long enough time for nuclear fusion to happen. And this experiment has demonstrated that it is possible. But also the problem with these reactors is the amount of energy that the reactor takes in is less than the amount of energy that it is producing. But this has been overcome, or at least demonstrated, in the recent experiment from Europe. Which leads to our second breakthrough. The Euro fusion team of researchers used the Joint European Torus Reactor, the JET, to produce a brief jolt of energy, sustained energy, of 59 megajoules for 5 seconds. And this obliterated their previous record, which was set over 20 years ago back in 1997 at the same facility of 21.7 megajoules. And what this experiment has demonstrated is a proof of concept, and it corroborated their experimental computer models. Now keep in mind, this was done on technology that was put into operation back in 1983. And then the China experiment was done on technology from 2006. And this is what I find most exciting right now about nuclear fusion, is because that third nuclear fusion reactor that is under construction in France that I mentioned earlier is a modern installation of this technology. So let's talk about that now. This is known as the ITER, the ITER, or whatever we want to call it. ITER, ITER. Let's just call it the ITER, which is the International Thermonuclear Experiment Reactor, which it really is a landmark project. And it's about 80% complete, and it'll go online around 2025. It will be somewhere between $18 and $22 billion to construct, making it one of the most expensive science projects of all time and one of the most complicated engineering projects in human history. So the ITER is building a specific type of reactor known as a tokamak, which is the same one used by China's East and Europeans' JET teams. Except the ITER tokamak is going to be essentially cutting edge and a larger scale than what they have available. And so the ITER tokamak reactor is going to weigh 29,000 tons, be able to create temperatures equal to 270 million degrees Fahrenheit, 10 times the heat of the sun's core. and provide a fusion energy output of 500 megawatts through an input of 50 megawatts. And that's the key thing. They're going to produce more energy than what goes in. That's the fundamental thing. If it's not producing more energy, it's not economically viable. So what is a Tokamak reactor and how does it reach these temperatures? I'm going to do my quick 2-second version of it. Then we're going to talk about what ITER defines this as. But fundamentally, a Tokamak uses extremely powerful magnetic fields, and the one that the ITER have will be over 200,000 times the strength of Earth's magnetic field to confine the plasma in a shape called a torus. And a torus is essentially a donut. Imagine taking a circle and rotating it 360 degrees about its axis to create that donut shape. That is a torus. And you know what? I'm just going to use the definition from ITER here. The Tokamak is an experimental machine designed to harness the energy of fusion. Inside a Tokamak, the energy produced through the fusion of atoms is absorbed as heat in the walls of the vessel. Just like a conventional power plant, a fusion power plant will use this heat to produce steam and then electricity by way of turbines and generators. The heart of a Tokamak is its donut-shaped vacuum chamber. Inside, under the influence of extreme heat and pressure, gaseous hydrogen fuel becomes a plasma, the very environment in which hydrogen atoms can be brought to fuse and yield energy. The charged particles of the plasma can be shaped and controlled by the massive magnetic coils placed around the vessel. Physicists use this important property to confine the hot plasma away from the vessel walls. The term Tokamak comes to us from a Russian acronym that stands for toroidal chamber with magnetic coils. And it was first developed by a Soviet research back in the late 1960s. ITER will be the world's largest Tokamak, twice the size of the largest machine currently in operation, with 10 times the plasma chamber volume. All right, so that concludes this episode of the Professional Engineer Podcast. I just wanted to dip our toes into this topic of nuclear fusion, and there's going to be many future episodes as I find experts in the field who are happy to come on and enlighten us on the incredible advancements that they are developing towards this sustainable form of energy. So thank you very much for your time. I hope you enjoyed, and I'll see you next week.